Hello. I'm so glad you're here tonight. Even if your eyes are heavy and your thoughts are beginning to slow, you can let yourself settle in now, wherever you are, perhaps beneath soft blankets, or in a quiet corner where the world feels far away. There's nothing you need to do but listen, and even listening can be gentle, the way you might listen to rain on a window or the hum of a distant road. Tonight, we're going to talk about something invisible, something that wraps around our entire planet and reaches out into the darkness of space. We're going to explore magnetic fields, those quiet, unseen forces that guide birds across continents, paint light across polar skies, and hold the very fabric of our world in a protective embrace. If you'd like more of these soft science stories to ease you into rest, you're welcome to follow along, but there's no pressure, no urgency. Just let yourself be here. Let's begin, slowly, with something vast and gentle. Magnetic fields are everywhere, though you cannot see them. They pass through your body right now, through the walls around you, through the air and the earth beneath your feet. They are silent. They have no color, no weight you can feel in your hand, and yet they shape the cosmos in ways both subtle and profound. To understand them is to understand an invisible architecture, a hidden scaffolding that organizes iron filings into elegant curves, that pulls compass needles toward the north, that shields us from harm we never consciously perceive. And the most soothing thing about magnetic fields is this: they have been here long before you, and they will remain long after, steady and patient, asking nothing of you but to exist within their gentle influence. Let's start with the Earth itself, this blue world turning quietly in space. Deep below your feet, far beneath the soil and stone, beneath the coolest layers of the mantle, there lies a core of molten iron. It churns slowly, driven by the planet's inner heat, swirling in great rivers of liquid metal. This motion, this endless circulation, generates something remarkable, a magnetic field that extends thousands of miles into space, wrapping our world in an invisible cocoon. You are inside that cocoon now. You've always been inside it. Every breath you've ever taken has been drawn within the embrace of Earth's magnetic field. And that thought, if you let it settle, can feel like the softest kind of safety. The Earth's magnetic field is not a perfect sphere. It bulges and warps, shaped by the solar wind, a stream of charged particles flowing out from the sun. On the side of Earth facing the sun, the magnetic field is compressed, pushed inward by the pressure of that stellar breeze. On the night side, it stretches out into a long tail, like a comet's trail, reaching far beyond the moon's orbit. Right now, as you rest, that tail is streaming silently away into the dark, a part of Earth's presence extending into the void. You are held within a structure that is both local and cosmic, both intimate and unimaginably vast. Imagine, if you will, the shape of a bar magnet. You may have seen one in school, surrounded by iron filings that arrange themselves into curved lines, arcing from one pole to the other. Earth's magnetic field looks much like that, though far larger and more complex. The lines of force emerge near the South Pole, loop outward through space, and descend again near the North Pole. These are called field lines, and though they are invisible, they are as real as the wind. Birds sense them. Sea turtles navigate by them. Even bacteria, tiny and ancient, contain crystals of magnetite that align with these lines, allowing them to orient themselves in the mud of lake bottoms and ocean floors. The world is full of quiet travelers who read the language of magnetism as naturally as you read these words. The strength of Earth's magnetic field is gentle. It is measured in units called Teslas, named after the inventor Nikola Tesla, though Earth's field is far weaker than the magnets you might use to hang notes on a refrigerator. At the surface, the field strength is about 50 microteslas, 50 millionths of a Tesla. That is enough to turn a compass needle, enough to guide a migrating goose across a continent, but not enough to tug at the iron in your blood or pull a paperclip from your hand. It is a whisper of a force, and yet it is enough. Enough to matter, enough to protect, enough to make life as we know it possible. This magnetic field is not static. It shifts and drifts over time, moving in ways both slow and strange. The magnetic North Pole, the point toward which compass needles aim, is not fixed. It wanders. Right now, It is moving across the Canadian Arctic toward Siberia, drifting at a pace of about 50 kilometers per year. That may sound fast, but on the scale of human life, it is almost imperceptible. Maps must be updated, navigation systems recalibrated, but the change is gradual, gentle, like the hands of a clock moving too slowly to see. There is no alarm in this. The poles have wandered for millions of years, tracing looping paths across the planet's surface, and the world continues, untroubled. Even more remarkable, the magnetic field sometimes reverses entirely. North becomes south. South becomes north. The last time this happened was about 780,000 years ago, an event recorded in ancient rocks where iron minerals, cooling and solidifying, froze the direction of the magnetic field in place like a memory. Scientists call this a geomagnetic reversal, and while it sounds dramatic, it is not a catastrophe. The process takes thousands of years, unfolding so slowly that no single generation would notice the change. During the transition, the field weakens and becomes more complex, sprouting multiple poles, but it does not vanish. Life persists. The sky does not fall. The Earth simply rearranges its invisible cloak, and the story continues. Why does this happen? The answer lies in that churning core of molten iron, a system so vast and chaotic that its behavior cannot be predicted with precision. The flow of liquid metal is driven by heat, by the planet's rotation, by the subtle interplay of forces deep below. Sometimes the flow organizes itself in one pattern, and sometimes it shifts to another. It is a natural rhythm, like the shifting of ocean currents or the slow dance of continents. There is no malice in it, no danger. It is simply the way a living planet breathes. The magnetic field does more than guide compasses. It protects us. High above the atmosphere, beyond the reach of weather and clouds, the solar wind rushes toward Earth at speeds of hundreds of kilometers per second. This wind is not air, but a plasma, a stream of electrons and protons torn from the sun's outer layers and flung into space. If Earth had no magnetic field, this plasma would strike the atmosphere directly, stripping away its gases over millions of years, the way Mars lost much of its own atmosphere long ago. But Earth's magnetic field deflects the solar wind, guiding it around our world, channeling it away. You are safe because of this. You have always been safe because of this. Sometimes, when the sun is particularly active, it releases great bursts of plasma, called coronal mass ejections. These are enormous clouds of charged particles that race across space, and when they reach Earth, they collide with the magnetic field. The field absorbs the impact, rippling and flexing like a drumhead struck by a soft mallet. The energy from this collision travels down the field lines toward the poles, and there, in the thin air of the upper atmosphere, it creates light. This is the aurora, the northern and southern lights. Curtains of green, red, violet, and blue shimmer across the polar skies, a visible manifestation of invisible forces. To see an aurora is to watch the magnetic field at work, painting the night with the energy of the sun. Auroras occur about 100 kilometers above the Earth's surface, in a region called the thermosphere. The colors depend on which gases are being excited by the incoming particles. Oxygen, when struck, glows green or red. Nitrogen produces blues and purples. The light is soft, often described as ghostly, and it moves, rippling, folding, dancing, because the magnetic field itself is dynamic, constantly adjusting to the push and pull of the solar wind. Indigenous peoples of the Arctic have watched these lights for thousands of years, weaving them into stories and songs. Some saw them as spirits, some as omens, some as the breath of the world itself. All of these interpretations hold a kind of truth, because the aurora is indeed the breath of Earth's magnetic field, made visible. You do not need to travel to the poles to be touched by the magnetic field. It is with you now. The atoms in your body contain charged particles, electrons orbiting nuclei, protons nestled at the center, and these particles interact, however faintly, with the field. The interaction is far too weak to feel, but it is real. In hospitals, powerful magnetic fields are used to create images of the inside of your body, a technique called magnetic resonance imaging. The field aligns the spin of hydrogen atoms in your tissues, and by measuring how they relax back into randomness, Doctors can see your organs, your brain, your beating heart. The same principle that guides a compass also reveals the hidden architecture of your own body. There is a continuity in this, a thread connecting the core of the earth to the core of you. Magnets themselves are ancient. Lodestone, a naturally magnetic mineral, was known to the Greeks and Chinese thousands of years ago. The Chinese called it loving stone because it seemed to reach out and attract iron. By the 11th century, they had learned to magnetize iron needles and float them on water, creating the first compasses. These simple tools transformed human civilization. Sailors could navigate even when the stars were hidden by clouds. Trade routes expanded. Explorers crossed oceans. The age of discovery was made possible, in part, by our understanding of the magnetic field, a force we still do not fully comprehend. Even today, the Earth is not the only world with a magnetic field. Jupiter, the giant of our solar system, has a magnetic field far stronger than ours, 20,000 times stronger at its surface. This immense field traps charged particles in vast belts of radiation, creating auroras on Jupiter that dwarf anything seen on Earth. Saturn, Uranus, and Neptune also have magnetic fields, each shaped by the internal dynamics of those distant worlds. Even the Sun has a magnetic field, one that twists and tangles as the Sun rotates, creating sunspots, solar flares, and the coronal mass ejections that occasionally disturb our own field. Magnetism is woven into the fabric of the solar system, a common thread linking worlds that will never touch. Mercury, the smallest planet, has a weak magnetic field, a faint echo of what Earth possesses. Mars once had a strong field, billions of years ago, but it faded as the planet's core cooled. Without that protective shield, the solar wind stripped away much of Mars's atmosphere, leaving it cold and dry. Venus, despite being similar in size to Earth, has no magnetic field at all, and its atmosphere, though thick, is slowly being eroded by the sun. These comparisons remind us of how fortunate we are. Earth's magnetic field is not a given. It is a gift of geology, of timing, of the particular conditions that allow a planet to remain dynamic and alive. The study of magnetic fields is called magnetism, and it is one of the four fundamental forces of nature, unified with electricity in a framework called electromagnetism. This force governs the behavior of charged particles, the flow of currents, the propagation of light. When you turn on a lamp, you are harnessing electromagnetism. When you listen to music, the speakers move because of magnets. The screen you might be looking at, the signals that carry information across the world. All of these depend on our ability to understand and manipulate magnetic fields. And yet, for all our technology, there is still mystery. We cannot predict geomagnetic reversals. We do not fully understand the dynamo in Earth's core. The magnetic field remains, in many ways, a gentle enigma. There is something deeply calming about the constancy of the magnetic field. It does not flicker like a flame or gust like the wind. It does not depend on the weather or the season. Day and night, summer and winter, the field is there, steady and patient. You can close your eyes and know that the same force guiding a compass in your hand is guiding a tern on its migration from pole to pole, is shaping the path of particles in the aurora, is holding the solar wind at bay. This is a kind of companionship, quiet and undemanding. The magnetic field asks nothing of you. It simply is. Even in the darkest depths of the ocean, the magnetic field reaches. Whales, sharks, and rays navigate using it, sensing the subtle variations in field strength and direction. Some fish have cells containing magnetite crystals, tiny compasses embedded in their bodies. Sea turtles, born on tropical beaches, swim out into the open ocean and somehow, years later, return to the very beach where they hatched. They read the magnetic field like a map written in forces instead of lines, in gradients instead of landmarks. This is navigation without sight, without sound, without thought as we understand it. It is pure, instinctive alignment with the hidden structure of the world. Humans, too, may have a faint sensitivity to magnetic fields, though the evidence is still emerging. Some studies suggest that certain proteins in our eyes, called cryptochromes, might be influenced by magnetism, allowing us to unconsciously sense direction. This ability, if it exists, is far weaker than in birds or turtles, buried beneath layers of culture and technology. But the possibility is tantalizing. It suggests that we are not entirely cut off from the magnetic world, that somewhere in the deep biology of our bodies, a thread still connects us to the ancient, invisible grid. The magnetic field also leaves traces in the rocks beneath our feet. When lava cools, iron-rich minerals align with the field and lock into place, recording its direction. By studying these rocks, scientists can reconstruct the history of the field over millions of years. They have discovered that the field has reversed hundreds of times, that its strength has waxed and waned, that it is far older than our species, older than the dinosaurs, older than the first forests. The field is a chronicle written in stone, a story of deep time that unfolds slowly, quietly, without words. There are places on Earth where the magnetic field is stronger, and places where it is weaker. Over the South Atlantic, there is a region called the South Atlantic Anomaly, where the field dips closer to the surface. Satellites passing through this region experience more radiation, and astronauts aboard the International Space Station sometimes see flashes of light, cosmic rays interacting with their retinas when they fly through it. This anomaly is not dangerous, just a quirk of the field's shape, a reminder that the field is not uniform but textured, varied, alive in its own way. The magnetic field also interacts with human technology in subtle ways. Pigeons, released in areas with strong magnetic anomalies, sometimes become disoriented. Compasses near large iron deposits can point in unexpected directions. Power grids, during intense geomagnetic storms, can experience surges as the changing magnetic field induces currents in long transmission lines. These are rare events, and engineers have learned to design systems that can withstand them. But they remind us that the field is not just a passive backdrop. It is an active participant in the world, shaping and being shaped by everything it touches. In the laboratory, scientists create magnetic fields far stronger than Earth's. Superconducting magnets, cooled to near absolute zero, can generate fields of 10 Teslas or more, hundreds of thousands of times stronger than the planet's field. These magnets are used to levitate trains, to contain fusion reactions, to probe the structure of matter at the smallest scales. Yet even these powerful fields are temporary, localized, dependent on constant energy input. Earth's field, by contrast, is sustained by the planet's own heat, by the slow cooling of the core over billions of years. It is a natural dynamo, requiring no maintenance, no fuel, no human intervention. It simply exists, as it has for eons. The concept of a field itself is abstract. You cannot hold a magnetic field in your hand, cannot pour it into a cup. It is a region of space where a force can be felt, a mathematical description of how magnets and charged particles will behave. And yet, fields are as real as anything else. They carry energy. They exert force. They shape the universe. To think about fields is to think about influence, about how one thing can affect another across empty space without touching. This is one of the deepest ideas in physics, and it applies not just to magnetism, but to gravity, to electricity, to the forces that hold atoms together. The universe is not a collection of isolated objects, but a web of fields, overlapping and interacting, each one a silent conversation between distant parts of the whole. There is a meditative quality to studying magnetic fields. They cannot be rushed. They reveal themselves slowly, through careful measurement, through the patient accumulation of data. A scientist mapping the Earth's magnetic field might spend years compiling observations, watching how the field shifts over time, searching for patterns in the noise. There is no dramatic moment of discovery, no sudden flash of insight, just the slow, steady work of understanding, piece by piece, until a picture emerges. This is science at its most contemplative, and there is something restful in that rhythm, something that mirrors the quiet patience of the field itself. Magnetic fields also play a role in the formation of stars and planets. In the vast clouds of gas and dust that drift between stars, magnetic fields thread through the material, influencing how it collapses under gravity. They can slow the collapse, allowing the cloud to fragment into multiple stars instead of one. They can channel material onto a growing protostar, shaping the disk from which planets will eventually form. Our own solar system, billions of years ago was shaped in part by magnetic forces, forces that helped determine where Earth would form, how much material it would gather, what kind of world it would become. The magnetic field is not just a feature of Earth. It is part of our origin story. Even in the human body, on the smallest scales, magnetism is at work. The electrons in your atoms have a property called spin, a quantum mechanical trait that gives them a tiny magnetic moment. These moments usually cancel each other out, but in certain materials, iron, cobalt, nickel, they align, creating a net magnetic field. This is why some metals are magnetic and others are not. It is a matter of internal alignment, of countless tiny magnets pointing in the same direction. There is a metaphor here, perhaps about cooperation, about how small individual contributions can add up to something much larger. But even without the metaphor, the physics is beautiful, elegant, a reminder that the world is ordered in ways both simple and profound. The Earth's magnetic field is not eternal. Billions of years from now, as the planet's core continues to cool, the dynamo will weaken and eventually stop. The field will fade, and Earth will become like Mars, unprotected, its atmosphere vulnerable. But this is so far in the future that it is almost irrelevant. The sun itself will have changed by then, swelling into a red giant, rendering the Earth uninhabitable long before the magnetic field fails. For now, for all of human history and all of human future that we can meaningfully imagine, the field is here. It is stable. It is strong enough. And that is all we need. There is comfort in the scale of these processes. The magnetic field operates on timescales so vast that your worries, your anxieties, your daily struggles are like ripples on the surface of a deep, calm ocean. The field does not notice them. It continues indifferent and benevolent, wrapping the world in its invisible arms. You are held within something larger than yourself, larger than your life, larger than the entire span of human civilization. And in that largeness, there is peace. The magnetic field also connects us to the cosmos in unexpected ways. Cosmic rays, high-energy particles from distant supernovae, and other violent events constantly rain down on Earth. The magnetic field deflects many of them, reducing the radiation dose we receive. Without it, life on the surface would be far more difficult, perhaps impossible. Every moment of your existence, the field is quietly protecting you from harm you never see, never feel, never think about. It is a guardian that never sleeps, never tires, never asks for thanks. And in that silent vigilance, there is something profoundly reassuring. Magnetism is also a source of beauty. The patterns formed by iron filings around a magnet are not random, but structured, elegant, almost artistic. The equations that describe magnetic fields, Maxwell's equations, named after the physicist James Clerk Maxwell, are considered among the most beautiful in all of science. They are simple, symmetric, powerful, unifying electricity and magnetism into a single coherent framework. To understand these equations is to see the world in a new way, to recognize that light itself is an electromagnetic wave, a ripple in the magnetic and electric fields propagating through space. Every photon that reaches your eye, every glimmer of starlight, every warm glow of a candle is a manifestation of electromagnetism. You are surrounded by it, immersed in it, made of it. The magnetic field is also a reminder of the interconnectedness of all things. A compass in your hand responds to the core of the Earth. The aurora in the Arctic is caused by the sun. The same force that holds a magnet to your refrigerator also shapes galaxies and governs the behavior of atoms. There are no isolated phenomena, no truly separate events. Everything touches everything else, through fields, through forces, through the invisible threads that weave the universe together. This is not mysticism but physics, and it is one of the most soothing truths science has to offer. You are not alone. You are part of a vast, intricate, interconnected whole. As you lie here, breathing slowly, you might imagine the magnetic field around you. It passes through you, through the walls, through the ground. It is always there, a silent presence, a gentle structure. You cannot feel it, but you can know it. And in that knowledge, there is a kind of companionship. The field is older than you, and it will outlast you, But right now, in this moment, you share the same space. You exist together, you and the field, in a quiet partnership that requires nothing but presence. The magnetic field is a gift of the planet, a consequence of its size, its composition, its history. Not all worlds have this gift. Not all worlds are shielded. But Earth does, and you are here, on this particular world, in this particular moment, held within the embrace of forces that have shaped life for billions of years. There is no need to do anything with this information. No need to act, to respond, to change. Just let it settle into your thoughts, a soft fact, a gentle truth. The magnetic field is here. You are here, and that is enough. The magnetic field that surrounds our planet extends far beyond what we can see or touch, reaching outward into space in a shape that scientists call the magnetosphere. This invisible bubble stretches tens of thousands of kilometers on the side facing the sun and trails behind Earth like a wind-blown tail for millions of kilometers on the night side. It is not a perfect sphere, but rather a teardrop, gently compressed by the constant pressure of the solar wind on one side and elongated into a long magnetotail on the other. This asymmetry gives our protective shield a dynamic, living quality, always responding to the breath of the sun. The magnetosphere is not empty space. Within its boundaries, charged particles spiral and dance along invisible lines of force, trapped in regions called the Van Allen radiation belts. These belts were discovered in 1958 by physicist James Van Allen, using data from the first American satellites. They consist of two main zones, an inner belt and an outer belt, each filled with protons and electrons that have been captured by Earth's magnetic field. These particles move in elegant helical paths, bouncing back and forth between the magnetic poles, held gently but firmly in their orbital prisons. The belts pulse and swell with the rhythm of solar activity, expanding when the sun is active and contracting during quieter periods. Between the two main radiation belts, there exists a region of relative calm, a slot where fewer particles reside. This gap is maintained by waves in the magnetic field itself, waves that scatter and remove particles, creating a quiet zone between the two more densely populated regions. It is a reminder that even in the seeming chaos of charged particles and magnetic forces, there are patterns, structures, and unexpected moments of emptiness. The universe arranges itself in ways that balance energy and motion, creating pockets of stillness even in the most active environments. The particles trapped in the Van Allen belts originate from two main sources. Some come from the solar wind, the stream of charged particles constantly flowing outward from the sun. Others are created when cosmic rays, high-energy particles from deep space, collide with atoms in Earth's upper atmosphere. These collisions produce cascades of secondary particles, some of which become trapped in the magnetic field. In this way, our magnetosphere is constantly being fed by both our own star and by the distant cosmos, a meeting place of near and far, of solar and galactic influences. The strength of Earth's magnetic field is not uniform across its surface. At the magnetic equator, the field is weaker, measuring about 30 microteslas. Near the magnetic poles, it is roughly twice as strong, around 60 microteslas. A microtesla is a very small unit, 1/millionth of a Tesla, the standard measure of magnetic field strength. To put this in perspective, a typical refrigerator magnet produces a field of about 5,000 microteslas. Earth's field is gentle by comparison, yet it is precisely this gentleness, spread over such vast distances, that makes it so effective at guiding and protecting. The magnetic field lines emerge from one magnetic pole, arc through space, and return to the other pole, creating loops that encircle the planet. These lines are invisible, but we can visualize them through their effects. Iron filings scattered around a bar magnet will arrange themselves along these lines, making the invisible visible. On a planetary scale, charged particles follow these same lines, spiraling along them like beads on a string. The field lines are densest near the poles and more spread out near the equator, which is why auroras, those glowing curtains of light, appear most often in polar regions. The Earth's magnetic field is generated deep within the planet, in the outer core, a layer of liquid iron and nickel that lies between 2,900 and 5,150 kilometers below the surface. This molten metal is in constant motion, driven by heat escaping from the even deeper inner core and by the rotation of the planet itself. As the liquid iron moves, it carries electric charges with it, and moving electric charges create magnetic fields. This process is called the geodynamo, a self-sustaining system where motion creates magnetism, and magnetism influences motion. The inner core at the very center of the Earth is solid despite being even hotter than the outer core. The immense pressure at that depth, over 3 million times the atmospheric pressure at sea level, forces the iron into a solid state. This inner core is about the size of the Moon, a sphere of crystalline iron spinning slightly faster than the rest of the planet. It is one of the most remote and inaccessible places in existence, yet its presence and its heat are essential to maintaining the dynamo that generates our protective magnetic field. The temperature in the outer core is estimated to be between 4,000 and 5,000 degrees Celsius, comparable to the surface of the Sun. Yet this incredible heat is contained, buried beneath thousands of kilometers of rock and metal. The energy that drives the geodynamo comes primarily from two sources: the slow cooling of the Earth over geological time, and the radioactive decay of elements like uranium, thorium, and potassium within the planet's interior. These processes release heat steadily, continuously, providing the energy needed to keep the outer core in motion. The movement of molten iron in the outer core is complex, involving large-scale convection currents, turbulent eddies, and rotational effects from the Earth's spin. This is not a simple, orderly flow, but a chaotic, three-dimensional dance of hot metal. Despite this complexity, the overall result is remarkably stable, a magnetic field that has persisted for billions of years. The fact that such order emerges from such chaos is one of the quiet wonders of planetary science, a reminder that complexity can give rise to enduring patterns. Computer simulations of a geodynamo require some of the most powerful supercomputers in the world. Scientists must solve equations that describe fluid motion, heat transfer, electromagnetic induction, and the effects of rotation, all interacting simultaneously. Even with modern computing power, these simulations are challenging and can take months to run. Yet they have yielded insights into how the magnetic field is generated and why it sometimes reverses. They show us that our magnetic field is not a static feature, but a dynamic, evolving phenomenon shaped by forces we are only beginning to fully understand. The magnetic poles, the points where the field lines are vertical, do not coincide with the geographic poles, the points defined by Earth's rotation axis. The North Magnetic Pole currently lies in the Arctic Ocean, north of Canada, while the South Magnetic Pole is off the coast of Antarctica. The offset between magnetic and geographic poles means that a compass does not point to true north, but to magnetic north. The difference between these two directions is called magnetic declination, and it varies depending on where you're on Earth. Magnetic declination has been important to navigators for centuries. In some locations, the declination is only a few degrees, but in others it can be 20 degrees or more. Sailors and explorers had to account for this difference when plotting their courses, using charts that showed the declination for different regions. Today, GPS has made navigation easier, but magnetic declination remains important for hikers, pilots, and anyone using a compass. It is a small but constant reminder that the Earth beneath us is not perfectly aligned, that there are layers and forces at work that complicate the simple picture we might imagine. The magnetic poles are not fixed in place. They wander over time, moving in response to changes in the flow of molten iron deep below. The North Magnetic Pole has been moving northward at an accelerating rate over the past few decades, traveling from northern Canada towards Siberia. It currently moves at about 50 kilometers per year, a pace that is fast by geological standards but slow enough that we barely notice in our daily lives. This wandering is a natural consequence of the dynamic geodynamo, a sign that the system is alive and constantly adjusting. Scientists track the movement of the magnetic poles using a combination of ground-based observatories, satellites, and mathematical models. The World Magnetic Model, updated every 5 years, provides the data needed for navigation systems worldwide. In 2019, an unscheduled update was necessary because the North Magnetic Pole was moving faster than expected. This was not a cause for alarm, but rather a testament to the sensitivity and precision of modern measurements. We live in an age where we can monitor the invisible forces of the Earth with remarkable accuracy, watching changes that would have been undetectable just a century ago. The magnetic field also varies in strength over time. Measurements taken over the past 2 centuries show that the overall strength of the field has decreased by about 10%. This decline is not uniform. Some regions have weakened more than others. Over the South Atlantic, there is an area known as the South Atlantic anomaly, where the field is significantly weaker than elsewhere. Satellites passing through this region experience higher levels of radiation, and astronauts aboard the International Space Station receive increased exposure when orbiting over this area. The South Atlantic anomaly is thought to be related to the structure of the magnetic field deep within the Earth. The field is not generated by a single center dipole, but by a complex arrangement of currents in the outer core. Some of these currents may be weaker or oriented differently beneath the South Atlantic, resulting in a local weakening of the field at the surface. This anomaly has been growing and moving westward over time, another sign of the dynamic nature of the geodynamo. It is a window into the deep interior, a place where the invisible architecture of the planet reveals itself through subtle changes in magnetic strength. The weakening of the magnetic field has led some to wonder whether we are heading toward a magnetic reversal, an event in which the north and south magnetic poles switch places. Such reversals have happened many times in Earth's history, recorded in the magnetic minerals of ancient rocks. When lava cools and solidifies, magnetic minerals within it align with the prevailing magnetic field, creating a permanent record of the field's direction at that time. By studying these magnetic signatures in rocks of different ages, scientists have reconstructed the history of Earth's magnetic field over hundreds of millions of years. Magnetic reversals are not rare on geological timescales. They occur irregularly, with intervals ranging from tens of thousands to millions of years. The last reversal, known as the Brunnsmachiama reversal, happened about 780,000 years ago. Before that, reversals were more frequent. The pattern is irregular, with no simple periodicity, which suggests that the geodynamo operates in a complex, possibly chaotic regime. Each reversal is unique, taking anywhere from a few thousand to tens of thousands of years to complete. During the transition, the magnetic field does not simply flip, it weakens, becomes more complex, and may even develop multiple poles before settling into a new configuration. There is no evidence that a magnetic reversal causes mass extinctions or catastrophic harm to life. The fossil record shows no correlation between reversals and major die-offs. Life has persisted through hundreds of reversals, adapting and continuing without interruption. During a reversal, the magnetic field does not disappear entirely. It becomes weaker and more complicated, but still provides some protection. The atmosphere also shields life from radiation, and together these defenses are sufficient to prevent widespread harm. This is reassuring, a reminder that the Earth has weathered many changes and that life is resilient. Some animals are sensitive to the magnetic field and use it for navigation. Sea turtles, for example, hatch on beaches and immediately head toward the ocean, guided by magnetic cues. As they grow, they migrate across vast distances, returning years later to the same beaches where they were born. They carry within them a magnetic map, an internal sense of the field's strength and direction that allows them to navigate with remarkable precision. This ability, called magnetoreception, is one of nature's quiet marvels, a sense we do not possess but can study and admire. Birds also use the magnetic field during migration. Species like the Arctic tern travel from pole to pole each year, covering distances of over 70,000 kilometers. They rely on a combination of cues, including the position of the sun and stars, but the magnetic field provides a reliable compass that works day and night, in all weather conditions. The mechanism behind avian magnetoreception is still being studied, but it is thought to involve specialized proteins in the bird's eyes that are sensitive to magnetic fields. These proteins may produce subtle changes in vision, allowing the birds to literally see the magnetic field as patterns of light or shadow overlaid on their visual world. Even some bacteria are magnetic. Magnetotactic bacteria contain chains of tiny magnetic crystals called magnetosomes, which act like internal compass needles. These bacteria live in sediments and water, and they use their magnetic sense to orient themselves along the Earth's magnetic field lines. This helps them navigate toward their preferred depth and chemical environment. The magnetosomes are made of magnetite or gragite, minerals that are naturally magnetic. The bacteria grow these crystals within their cells, a process that is still not fully understood, but represents one of the simplest and most elegant examples of biological magnetism. The study of magnetotactic bacteria has implications beyond biology. Scientists are interested in how organisms can create such perfectly shaped magnetic crystals, a process that might inspire new technologies for manufacturing nanoscale materials. These bacteria also leave behind magnetic signatures in sediments, which can be used to study past environmental conditions. In this way, even the smallest organisms contribute to our understanding of the Earth's magnetic history, adding their quiet testimony to the record written in stone. Magnetite, the mineral that gives these bacteria their magnetic sense, is also found in rocks around the world. It is one of the most magnetic naturally occurring minerals, and it has been known to humans for thousands of years. Ancient peoples discovered that certain stones, called lodestones, could attract iron. These lodestones are pieces of magnetite that have been naturally magnetized, often by lightning strikes. The word magnet itself comes from Magnesia, a region in ancient Greece where such stones were found. The discovery of magnetism is lost in prehistory, but its practical use began with the invention of the magnetic compass. The earliest compasses, developed in China over 1,000 years ago, consisted of a piece of magnetized iron floating on water or balanced on a pivot. This simple device revolutionized navigation, allowing sailors to determine direction even when the sun and stars were hidden by clouds. The compass spread along trade routes, reaching the Islamic world in Europe, where it became an essential tool for exploration. It is remarkable that such a simple interaction between a mineral and the Earth's field could have such profound effects on human history. The Earth's magnetic field also interacts with the solar wind in ways that create beautiful and complex phenomena. When charged particles from the sun reach the magnetosphere, they can be funneled along the magnetic field lines toward the polar regions. There, they collide with atoms and molecules in the upper atmosphere, transferring energy and causing them to glow. This glow is the aurora, known as the aurora borealis in the northern hemisphere and the aurora australis in the southern hemisphere. The colors depend on which gases are involved and at what altitude the collisions occur. Oxygen produces green and red light, while nitrogen produces blue and purple hues. Auroras are most commonly seen in an oval-shaped region around each magnetic pole, known as the auroral oval. This region expands and contracts with solar activity. During periods of high solar activity, when the sun releases powerful bursts of particles in events called coronal mass ejections, the auroral oval can expand, bringing auroras to lower latitudes where they are rarely seen. People in northern Europe, Canada, and Alaska see auroras regularly, but during strong geomagnetic storms, they have been visible as far south as the Mediterranean, the southern United States, and even the tropics. The light of an aurora is gentle, often described as shimmering or dancing. It can appear as arcs, curtains, rays, or diffuse glows, changing shape and intensity over minutes or hours. Watching an aurora is a meditative experience, a slow-motion display of natural beauty that connects the observer to the vast processes occurring in space. The light is silent, yet it feels as though the sky is alive, breathing and shifting in response to invisible forces. For those who have witnessed a strong aurora, it is an unforgettable experience, a reminder of the dynamic connection between Earth and Sun. The colors of the aurora are determined by physics that is both simple and elegant. When a charged particle strikes an oxygen atom at high altitude, around 200 to 300 kilometers above the surface, the collision excites the atom, boosting one of its electrons to a higher energy level. When the electron falls back to its original level, it releases the excess energy as a photon of light. For oxygen, this photon is typically green, the most common color in auroras. At even higher altitudes, above 300 kilometers, oxygen can emit red light. Nitrogen, which is more abundant in the atmosphere, produces blue and purple light, often seen at the lower edges of auroral displays. The energy required to produce an aurora is immense. A strong auroral display can involve billions of watts of power, comparable to the output of a large power plant. Yet this energy is spread over vast areas of the sky, so the light appears soft and diffuse rather than blinding. The atmosphere absorbs most of the energy, heating slightly in the process, but not enough to cause noticeable effects on weather or climate. The aurora is a spectacle that occurs at the boundary between Earth and space, in the thin upper layers of the atmosphere where the air is too thin to breathe, but still thick enough to glow. Auroras are not unique to Earth. Other planets with magnetic fields and atmospheres also experience auroral displays. Jupiter, with its powerful magnetic field and rapid rotation, has auroras that are far more intense than Earth's. They occur near Jupiter's poles and are driven not only by the solar wind, but also by volcanic activity on Io, one of Jupiter's moons. Io's volcanoes eject sulfur and oxygen into space, and these particles become ionized and trapped in Jupiter's magnetic field, eventually spiraling down into the atmosphere to create brilliant auroras. Observing these distant light shows with telescopes and spacecraft reminds us that magnetism and auroras are universal phenomena, occurring wherever the right conditions exist. Saturn also has auroras, observed by the Hubble Space Telescope and by spacecraft that have visited the planet. Saturn's auroras are influenced by the solar wind and by interactions with its rings and moons. Even planets without global magnetic fields, like Mars and Venus, can have localized auroral displays. On Mars, auroras occur over regions where ancient magnetic fields are frozen into the crust. These crustal magnetic fields are remnants of a time when Mars had a global dynamo, now long extinct. The auroras on Mars are faint and patchy, visible only in ultraviolet light, but they are a ghostly reminder of the planet's magnetic past. The solar wind, which plays such a crucial role in shaping Earth's magnetosphere and creating auroras, is itself a fascinating phenomenon. It is a stream of charged particles, mostly electrons and protons, that flows outward from the sun at speeds of 300 to 800 kilometers per second. The solar wind originates in the sun's corona, the outermost layer of the solar atmosphere, where temperatures reach millions of degrees. At these extreme temperatures, the gas is so energized that the sun's gravity cannot hold it, and it streams away into space, filling the solar system with a tenuous plasma. The density of the solar wind is very low, only a few particles per cubic centimeter by the time it reaches Earth. For comparison, the air we breathe contains about 10 to the power of 19 molecules per cubic centimeter. Yet despite its low density, the solar wind carries energy and momentum, and it exerts pressure on anything it encounters. This pressure compresses the day side of Earth's magnetosphere and stretches the night side into a long tail. The interaction between the solar wind and the magnetosphere is a delicate balance, a continuous push and pull that shapes the space environment around our planet. The sun is not constant. It has an activity cycle lasting about 11 years, during which the number of sunspots, solar flares, and coronal mass ejections rises and falls. At solar maximum, the sun is covered with dark sunspots, and eruptions are frequent. At solar minimum, the sun is quieter, with fewer spots and less activity. This cycle affects the solar wind and, consequently, the space environment around Earth. During solar maximum, geomagnetic storms are more common, auroras are more frequent and intense, and satellites and power grids are at greater risk of disruption. Geomagnetic storms occur when a burst of solar wind, often associated with a coronal mass ejection, reaches Earth and disturbs the magnetosphere. The enhanced flow of particles can compress the magnetosphere, inject energy into the Van Allen belts, and cause rapid changes in the magnetic field at Earth's surface. These changes can induce electric currents in long conductors, such as power lines and pipelines, potentially causing damage. In 1989, a severe geomagnetic storm caused a blackout in Quebec, leaving millions without power for hours. Such events are rare, but they remind us that we live in a connected system where events on the sun can have tangible effects on Earth. Despite these occasional disruptions, the magnetic field is overwhelmingly beneficial. It has shielded life on Earth for billions of years, allowing the atmosphere to persist and life to evolve. Without the magnetic field, the solar wind would gradually strip away the atmosphere, as has happened on Mars. Mars once had a thicker atmosphere and liquid water on its surface, but when its magnetic field disappeared, the solar wind eroded the atmosphere over millions of years. Today, Mars is cold and dry, with only a thin atmosphere remaining. The contrast between Earth and Mars highlights the importance of the magnetic field as a guardian of habitability. The magnetic field also affects the chemistry of the upper atmosphere. Charged particles trapped in the magnetosphere can collide with atmospheric molecules, breaking them apart and creating ions and free radicals. These reactive species participate in complex chemical reactions, influencing the composition and structure of the ionosphere, a layer of the atmosphere between 60 and 1,000 kilometers altitude. The ionosphere is important for radio communication, as it reflects certain radio waves, allowing them to travel beyond the horizon. Variations in the ionosphere, driven by solar activity and the magnetic field, can affect the quality and range of radio signals. The study of the magnetic field and its interactions with the sun and space is called space weather. Just as meteorologists study weather in the lower atmosphere, space weather scientists monitor conditions in the magnetosphere, ionosphere, and solar wind. They use data from ground-based observatories, satellites, and solar telescopes to track solar activity and predict geomagnetic storms. Space weather forecasts help satellite operators, power companies, and airlines prepare for potential disruptions. This is a relatively new field, but it is growing in importance as our technological infrastructure becomes more dependent on space-based systems. One of the key tools for studying space weather is the fleet of satellites that orbit Earth and monitor the sun. The Advanced Composition Explorer, or ACE, sits at a special point in space called the L1 Lagrange point, about 1.5 million kilometers from Earth toward the sun. At this location, the gravitational pull of the Earth and Sun balance, allowing the satellite to remain in a stable position. ACE measures the solar wind and provides advance warning of incoming disturbances, giving scientists and operators about 15 to 60 minutes to prepare before the effects reach Earth. This early warning system is a testament to human ingenuity, a way of using our understanding of physics to anticipate and mitigate natural hazards. Other satellites, such as those in the GOES and Themis missions, study the magnetosphere itself, measuring magnetic fields, particle populations, and electric currents. Together, these missions provide a comprehensive picture of the space environment, revealing the intricate and ever-changing interactions between the sun, the solar wind, and Earth's magnetic field. The data they collect are freely available to researchers worldwide, contributing to a global effort to understand and predict space weather. The magnetic field also plays a role in the history of plate tectonics, the slow movement of Earth's crustal plates. As new oceanic crust forms at mid-ocean ridges, molten rock rises from the mantle, cools, and solidifies. Magnetic minerals in the rock record the direction of the magnetic field at the time of formation. As the crust spreads away from the ridge, it creates a pattern of magnetic stripes, alternating between normal and reverse polarity, corresponding to periods when a magnetic field had its current orientation and periods when it was reversed. This pattern, discovered in the 1960s, provided key evidence for the theory of plate tectonics and revolutionized our understanding of Earth's geology. The magnetic stripes are symmetrical on either side of the mid-ocean ridges, a beautiful pattern that reflects the steady, slow process of seafloor spreading. By measuring the width of the stripes and knowing the timing of magnetic reversals, scientists can calculate the rate at which new crust is formed. This rate varies from a few centimeters to several centimeters per year, depending on the ridge. Over millions of years, this slow process has reshaped the surface of the Earth, opening and closing ocean basins, building mountain ranges, and moving continents. The magnetic field, by recording these movements, has become an essential tool for understanding the dynamic nature of our planet. Paleomagnetism, the study of ancient magnetic fields recorded in rocks, has also provided insights into the movement of continents over geological time. By measuring the magnetic orientation of rocks from different continents and different ages, scientists can reconstruct the positions of the continents in the past. This has revealed that the continents were once joined together in supercontinents, such as Pangaea, which existed about 300 million years ago. Pangaea eventually broke apart, and the continents drifted to their current positions, a process that continues today. The magnetic record is like a time-lapse movie of Earth's surface, showing the slow dance of continents across the globe. The magnetic field of Earth extends far beyond what we can see or touch, reaching out into space in ways that continue to surprise and comfort us. When we think of protection, we often imagine walls or shields, but the magnetosphere is neither solid nor visible. It is a region of influence, a zone where Earth's magnetic presence is stronger than the magnetic forces arriving from the Sun and the wider cosmos. This boundary, called the magnetopause, is not fixed. It breathes. It expands and contracts with the rhythm of the solar wind, moving closer to Earth when the Sun is active and stretching farther out during quieter times. On the side facing the Sun, the magnetopause hovers about 10 Earth radii away, roughly 60,000 kilometers above the surface. On the night side, the field is drawn out into a long tail, the magnetotail, that extends for millions of kilometers downstream, like a banner trailing in a gentle cosmic breeze. This tail is a place of slow, silent processes where particles are stored, sorted, and sometimes sent spiraling back toward Earth in glowing arcs. Within the magnetosphere, there are regions of surprising stillness. The plasmasphere is one such place, a donut-shaped zone of cool, dense plasma that rotates with the Earth. It lies inside the main body of the magnetosphere, co-rotating quietly with our planet's spin. The particles here are cold by space standards, moving slowly, bound to Earth's rotation by magnetic field lines. The plasmasphere is densest near Earth and thins gradually outward, ending at a boundary called the plasmapause. Beyond this edge, the plasma becomes hotter and more turbulent, influenced more by the Sun than by Earth. The plasmapause itself can shift, expanding and contracting with geomagnetic activity, a soft threshold between the calm inner zone and the more dynamic outer regions. Scientists study this boundary not with their eyes, but with radio waves and satellites, listening to the way electromagnetic signals change as they pass through different densities of charged particles. Magnetic field lines are often drawn as smooth, elegant curves and diagrams, and while this is a simplification, it captures something true. Field lines represent the direction a magnetic force would guide a lone North Pole if one could exist in isolation. Near Earth's equator, these lines arc outward into space, forming loops that connect the northern and southern hemispheres. Near the poles, the lines plunge steeply downward, diving into the planet. Charged particles, such as electrons and protons, spiral along these lines, trapped by the magnetic force. They cannot easily cross from one line to another. Instead, they follow the field's geometry, bouncing back and forth between the magnetic mirrors near the poles. This trapping creates the radiation belts and gives structure to the auroras. The particles move quickly along the field lines, but drift slowly around the Earth, creating currents that encircle the planet. These ring currents are invisible rivers of charge, flowing westward around the equator, contributing to the overall shape and strength of the magnetosphere. The interaction between the solar wind and Earth's magnetic field is not a collision, but a conversation. The solar wind carries its own magnetic field, frozen into the plasma as it streams outward from the Sun. When this interplanetary magnetic field encounters Earth's magnetosphere, the two fields press against each other. If the solar wind's field is oriented southward, opposite to Earth's northward field at the equator, something remarkable happens. The field lines can reconnect. Magnetic reconnection is a process in which field lines from two different sources break and rejoin in new configurations, releasing energy in the process. This is not a violent explosion, but a smooth rearrangement, a kind of magnetic handshake. When reconnection occurs on the day side of the magnetosphere, it allows some solar wind particles to enter the magnetosphere, sliding along the newly connected field lines. These particles are then carried around to the night side, where they can reconnect again, flinging energy and particles back toward Earth. This process powers geomagnetic storms and intensifies the auroras. But it happens gradually, over minutes and hours, a slow dance of invisible forces. Geomagnetic storms are often described with urgency, but from the perspective of the field itself, they are simply adjustments. When a strong burst of solar wind arrives, carrying a southward magnetic field, reconnection accelerates. More particles enter the magnetosphere, and the ring current intensifies. The added current creates its own magnetic field, which opposes Earth's field, temporarily weakening it at the surface. This weakening is what we measure during a geomagnetic storm. The disturbance can last for hours or days, but the field does not break. It bends, it adjusts, it absorbs the energy. Auroras become more frequent and stretch to lower latitudes. Compasses may shift slightly. Sensitive electronics in space can be affected. But for most of us on the ground, the storm is invisible, a quiet recalibration happening high above. The field has weathered such storms for billions of years, and it continues steady and resilient. The study of these storms has taught us much about the magnetosphere structure. Scientists use a network of ground-based magnetometers, instruments that measure the strength and direction of the magnetic field at Earth's surface. When a geomagnetic storm occurs, these instruments detect the changes in unison, revealing the global nature of the disturbance. Data from satellites adds another layer, showing how the magnetosphere compresses, how currents shift, how particles are accelerated. Together, these observations build a picture of a dynamic, responsive system. The magnetosphere is not a static bubble, but a living boundary, constantly negotiating with the space environment. And yet, despite all this activity, the overall field remains remarkably stable. The core continues to churn, the dynamo continues to operate, and the field continues to shield us. One of the most calming aspects of the magnetic field is its predictability over human timescales. While the field does wander and reverse over geological time, on the scale of a human life, it is steady. The North Magnetic Pole drifts, yes, but slowly enough that we can track it, update our maps, and adjust our navigation systems. The field strength varies slightly from year to year, but these changes are small, a few percent per century. For anyone standing on the surface, the magnetic field feels constant. A compass needle points north today, as it did yesterday, as it will tomorrow. This constancy is a gift. It allows migratory birds to navigate across continents, sea turtles to find their way across oceans, and humans to explore the world with confidence. The field is a reliable guide, a silent companion that has been with us since long before we understood it. The connection between the magnetic field and life extends beyond navigation. Some researchers have explored whether the magnetic field influences biological rhythms, health, or even consciousness. The evidence is subtle and still debated, but there are hints. Certain bacteria contain chains of magnetite crystals, which align with the magnetic field and help the bacteria orient themselves in sediment. These magnetotactic bacteria are found in lakes, oceans, and soils around the world, proof that life can sense and respond to magnetism at the cellular level. Whether larger organisms, including humans, have similar sensitivities is less clear. Some studies suggest that homing pigeons have magnetite-based sensors in their beaks, while others point to light-sensitive proteins in the eyes that may detect magnetic fields through quantum effects. The science is still unfolding, but the possibility is intriguing that we are all, in some quiet way, attuned to the magnetic presence of our planet. The magnetic field also plays a role in the formation of certain minerals and rocks. When lava cools and solidifies, iron-rich minerals within the rock align with the ambient magnetic field, creating a permanent record of the field's direction and strength at that moment in time. This process, called thermoremnant magnetization, is the foundation of paleomagnetism, the study of ancient magnetic fields. By examining rocks of different ages, scientists can reconstruct the history of Earth's magnetic field, revealing not only reversals, but also changes in intensity and the movement of continents. This record is written in stone, a silent archive that stretches back billions of years. Each layer of basalt in the ocean floor, each ancient lava flow, each sedimentary deposit holds a memory of the field. It is a library without words, read not with eyes, but with magnetometers, and it tells a story of a planet in constant, slow motion. The ocean floor itself is a testament to the magnetic field's influence. As new crust forms at mid-ocean ridges, it cools and locks in the current magnetic orientation. As the seafloor spreads, this crust moves away from the ridge, carrying its magnetic signature with it. When the field reverses, the newly forming crust records the opposite polarity. Over millions of years, this creates a pattern of magnetic stripes, alternating bands of normal and reverse polarity, symmetrically arranged on either side of the ridge. This pattern was one of the key pieces of evidence for the theory of plate tectonics. It showed that the ocean floor was young, dynamic, and constantly being renewed. The magnetic field, invisible and intangible, had left a clear, readable mark on the planet's surface, a map of motion written in stone. The field's influence extends even to the atmosphere. While the magnetic field itself does not directly affect neutral air molecules, it does interact with the ionosphere, a layer of the atmosphere where ultraviolet radiation from the sun ionizes atoms and molecules, creating a sea of free electrons and ions. The ionosphere is influenced by both solar radiation and the magnetic field. Charged particles trapped in the magnetosphere can precipitate into the ionosphere, especially during geomagnetic storms, enhancing ionization and creating disturbances. These disturbances can affect radio communication, GPS signals, and even power grids. But they also create beauty. The auroras occur in the ionosphere, where incoming particles collide with oxygen and nitrogen, exciting them to emit light. The colors and shapes of the auroras are determined by the type of gas, the altitude, and the energy of the incoming particles, all choreographed by the invisible hand of the magnetic field. There is something deeply reassuring about the fact that the magnetic field connects the ground beneath our feet to the space above our heads, and even to the sun itself. It is a reminder that we are not isolated, but part of a larger system. The field lines that arc through the sky above you also thread through the earth below you. The same force that guides a compass needle also shapes the paths of particles streaming from the sun. The field is a bridge between scales, linking the atomic and the planetary, the local and the cosmic. It is a unifying presence, subtle and pervasive, woven into the fabric of our world. The magnetic field also has a calming effect on our understanding of time. Geological time is vast, almost incomprehensible, but the magnetic field gives us markers, reference points. Each reversal is an event, a moment in deep time that can be identified and dated. By studying the magnetic stripes on the ocean floor, or the magnetization of ancient rocks, we can construct a timeline of Earth's history. We can see when continents collided, when oceans opened, when volcanic activity surged. The field is a clock, ticking not in seconds but in millions of years, and it helps us make sense of the planet's long, slow story. There is comfort in this perspective. Our lives are brief, but we are part of continuity that stretches back to the very beginning. The magnetic field is also a source of scientific curiosity and wonder. Despite centuries of study, there is still much we do not fully understand. The exact mechanisms that trigger a reversal, the reasons for variations in field strength, the details of the dynamo process in the outer core, all of these remain active areas of research. Scientists use computer simulations to model the behavior of the liquid iron in the core, attempting to recreate the conditions that generate the field. These simulations are complex, requiring supercomputers and sophisticated mathematics, but they are gradually revealing the inner workings of the geodynamo. Each new discovery adds to our understanding, and each question answered raises new ones. The field is a puzzle, but a gentle one, inviting exploration rather than demanding urgency. One of the most intriguing recent discoveries is the detection of magnetic fields on other planets and moons. Mercury has a weak magnetic field, generated by a small, partially molten core. Jupiter has an enormous magnetic field, far stronger than Earth's, generated by metallic hydrogen in its interior. Saturn, Uranus, and Neptune also have magnetic fields, each with unique characteristics. Some moons, like Ganymede, have their own internal magnetic fields, while others, like Europa, generate magnetic fields through the interaction of their subsurface oceans with Jupiter's magnetic field. These discoveries show that magnetic fields are common in the solar system, each shaped by the internal structure and composition of the body that generates it. Studying these fields helps us understand not only those distant worlds, but also our own. Earth's magnetic field is not unique, but it is special, finely tuned by billions of years of evolution to support and protect life. Mars, by contrast, lacks a global magnetic field today, though it once had one. Evidence from Mars orbiters shows that ancient rocks on Mars are magnetized, indicating that a dynamo once operated in the Martian core. But sometime in the planet's history, the dynamo shut down, perhaps because the core cooled and solidified, or because the convection patterns changed. Without a magnetic field, Mars lost much of its atmosphere to the solar wind, which stripped it away over millions of years. The planet became cold, dry, and barren. This history is a sobering reminder of the magnetic field's importance. It is not just a curiosity, but a necessity for maintaining a thick atmosphere and a stable climate. Earth's magnetic field has helped preserve the conditions for life, and its continued operation is a quiet blessing. The magnetic field also influences the way we explore space. Spacecraft traveling beyond Earth's magnetosphere must contend with higher levels of radiation, since they no longer have the field's protection. Astronauts on the International Space Station are still within the magnetosphere, shielded from much of the solar wind and cosmic rays. But missions to the Moon, Mars, or beyond require careful planning to minimize radiation exposure. The magnetic field is a boundary, a threshold between the relative safety of near-Earth space and the harsher environment beyond. Understanding this boundary is essential for the future of human space exploration. It is another way the field shapes our relationship with the cosmos. There is also a quiet beauty in the mathematics of magnetic fields. Maxwell's equations, formulated in the 19th century, describe how electric and magnetic fields are generated and how they interact. These equations are elegant, symmetrical, and deeply powerful. They predict the existence of electromagnetic waves, including light, and they unify electricity and magnetism into a single framework. The magnetic field of Earth obeys these same equations, a local manifestation of universal laws. There is something soothing in this universality, the idea that the same principles that govern a bar magnet on a table also govern the vast magnetosphere of a planet. The universe is governed by rules, and those rules are knowable, expressible, and beautiful. The field geometry is also a source of calm contemplation. Magnetic field lines never cross, and they always form closed loops, though some of those loops may extend far into space. Near a bar magnet, the loops are small and tight. Near Earth, they stretch across hemispheres and into the magnetosphere. But the principle is the same. The field is continuous, smooth, and orderly. There are no gaps, no breaks, no discontinuities. This continuity is part of what makes the field so reliable. It is everywhere, always, a gentle presence that fills space without interruption. The field also has a role in the history of science and exploration. The invention of the magnetic compass revolutionized navigation, allowing sailors to venture far from shore with confidence. The compass needle, a simple piece of magnetized iron, became a lifeline, a connection to the invisible field that encircles the planet. Without the compass, the age of exploration might have unfolded very differently. Maps might have remained incomplete, trade routes uncertain, cultures more isolated. The magnetic field, through the humble compass, helped knit the world together. It is a reminder that science and technology are not separate from human experience, but deeply intertwined with it. The declination of the compass, the angle between magnetic north and true north, varies depending on where you are on Earth. In some places, the two norths align closely. In others, the difference can be many degrees. Navigators must account for this declination when plotting courses, adjusting their headings to compensate. The declination itself changes over time as the magnetic poles wander, so maps and charts must be updated periodically. This slow drift is another reminder of the field's dynamic nature. It is not frozen in place, but alive, shifting, responding to the currents deep below. Yet this motion is so gradual that it requires careful measurement to detect. For most purposes, the field is stable enough to rely on, a dependable guide through an ever-changing world. The magnetic field also plays a role in the aurora's colors. Oxygen, when struck by high-energy particles, emits green light, the most common auroral color. At higher altitudes, where the atmosphere is thinner, oxygen emits red light. Nitrogen produces blue and purple hues. The altitude at which the particles collide with the atmosphere determines which colors appear, and this altitude is influenced by the energy of the particles and the geometry of the magnetic field. The result is a spectrum of colors, layered and shifting, painting the night sky with soft, glowing curtains. The auroras are a visible manifestation of invisible processes, a gift from the magnetic field to those who live at high latitudes. Auroras are not unique to Earth. Jupiter's auroras are the most powerful in the solar system, driven by the planet's rapid rotation and strong magnetic field. Saturn's auroras are influenced by the solar wind and by particles from its moon Enceladus. Even Mars, which lacks a global magnetic field, has localized auroras over regions where ancient crustal magnetism remains. These auroras are faint and patchy, but they exist, a ghostly reminder of the planet's magnetic past. Studying auroras on other planets helps scientists understand the underlying physics, the ways magnetic fields and charged particles interact across different environments. Each aurora is unique, but all share the same basic mechanism. Particles guided by magnetic fields, colliding with atmospheric gases, releasing light. The magnetic field is also a subject of cultural significance. Many ancient cultures noticed the behavior of lodestones and magnetized needles, and some incorporated magnetism into their cosmologies and navigation practices. The Chinese were among the first to use magnetic compasses for navigation, as early as the 11th century. In Europe, the compass became widespread in the 13th century, transforming maritime travel. The magnetic field, though invisible, became a part of human culture, a tool and a mystery. It inspired scientific inquiry, artistic metaphor, and philosophical reflection. The idea that an invisible force could guide a needle, that the Earth itself was a magnet, challenged and expanded human understanding of nature. The field's invisibility is part of its magic. We cannot see it, hear it, or feel it directly, yet it is always there, shaping the space around us. This invisibility makes it easy to forget, to overlook, but it also makes it a perfect subject for quiet contemplation. The magnetic field is a reminder that much of the universe operates beyond the reach of our senses, that reality is richer and more complex than what we can directly perceive. It invites us to trust in instruments, in mathematics, in the accumulated knowledge of science. It teaches us humility and wonder. The field also connects us to the deep interior of the planet. The outer core, where the field is generated, lies nearly 3,000 kilometers below the surface. We will never visit it, never see it, never touch it. Yet we know it is there, churning and convecting, because of the magnetic field it creates. The field is a messenger from the depths, carrying information about conditions we can only infer. It is a bridge between the inaccessible interior and the surface we inhabit, a link forged by physics and revealed by careful observation. The magnetic field is also remarkably efficient. The energy required to maintain the geodynamo comes from the slow cooling of the core and the solidification of the inner core, processes that release heat and drive convection. This energy is modest compared to the total heat flow from Earth's interior, yet it is enough to sustain a magnetic field that extends hundreds of thousands of kilometers into space. The field is a testament to the power of organized motion, of coherent currents flowing in concert. It shows that even small amounts of energy, properly harnessed, can have vast effects. The field's strength at Earth's surface is about half a Gauss, or 50 microteslas, a modest value by laboratory standards. A refrigerator magnet is much stronger. Yet this weak field is enough to deflect the solar wind, trap radiation belts, and guide compass needles. It is a reminder that strength is not always about intensity, but about reach and persistence. The field is weak but vast, gentle but effective. It does not shout. It hums quietly, doing its work without fanfare. The field also has a role in the carbon cycle and climate, though the connections are indirect and subtle. By protecting the atmosphere from erosion by the solar wind, the field helps maintain the pressure and composition necessary for liquid water and life. Liquid water, in turn, is essential for weathering rocks, which removes carbon dioxide from the atmosphere and stores it in minerals. This process, operating over millions of years, helps regulate Earth's climate. The magnetic field is one thread in a complex web of interactions that keep the planet habitable. It is not the only factor, but it is an important one, a quiet guardian working in the background. The field's role in protecting the ozone layer is another indirect but important connection. The ozone layer, located in the stratosphere, absorbs harmful ultraviolet radiation from the sun. High-energy particles from space, if they reach the atmosphere in large numbers, can break apart ozone molecules, thinning the layer. The magnetic field reduces the number of such particles that reach the atmosphere, helping to preserve the ozone layer. This protection is not absolute. Solar storms can still cause temporary ozone depletion at high latitudes, but it is significant. The field and the ozone layer work together, two invisible shields that allow life to flourish on the surface. The field also influences the distribution of cosmic rays, high-energy particles that originate outside the solar system. Cosmic rays are mostly protons, traveling at nearly the speed of light, and they can penetrate deep into the atmosphere, creating cascades of secondary particles. The magnetic field deflects some of these cosmic rays, reducing the radiation dose at the surface. The amount of deflection depends on the particle's energy and charge, and on the strength and orientation of the field. Near the magnetic equator, where the field lines are horizontal, cosmic rays must have higher energy to penetrate. Near the poles, where the field lines are vertical, lower energy cosmic rays can reach the atmosphere more easily. This creates a latitude-dependent variation in cosmic ray intensity, a subtle gradient shaped by the invisible hand of the magnetic field. The study of cosmic rays and their interaction with the magnetic field has led to important discoveries in particle physics. Cosmic rays were among the first sources of high-energy particles available for study, long before particle accelerators were built. Scientists studying cosmic rays discovered the positron, the muon, and other fundamental particles. The magnetic field, by guiding and deflecting these particles, played a role in shaping the experiments and observations that advanced our understanding of the subatomic world. It is another example of how the field connects different scales and domains of knowledge, from the planetary to the quantum. The field also has a role in space weather forecasting. By monitoring the sun's activity and the properties of the solar wind, scientists can predict when geomagnetic storms are likely to occur. These forecasts help satellite operators, power grid managers, and airlines prepare for potential disruptions. The forecasts are not perfect. Space weather is complex and chaotic, but they are improving as our understanding of the Sun-Earth connection deepens. The magnetic field is both the subject of these forecasts and the reason they matter. It is the interface where solar activity meets terrestrial technology, a boundary that requires constant vigilance and study. The field's variability over geological time also offers insights into the workings of the deep Earth. By studying the timing and duration of magnetic reversals, scientists can infer changes in the dynamics of the outer core. Some periods of Earth's history had frequent reversals, while others had long stretches of stable polarity. These variations may be linked to changes in the rate of heat flow from the core, or to shifts in the patterns of convection. The magnetic record is a window into processes that are otherwise hidden, a way of reading the planet's internal history. The field is also a source of inspiration for artists and writers. The idea of invisible forces shaping the world, of unseen currents flowing through the Earth, has a poetic resonance. The Auroras, with their shifting colors and ethereal beauty, have inspired countless works of art, music, and literature. The magnetic field itself, though invisible, has become a symbol of connection, guidance, and protection. It is a reminder that the most important things are often the ones we cannot see. The field's constancy over human timescales is a source of comfort in a changing world. While climates shift, landscapes erode, and societies rise and fall, the magnetic field remains a quiet presence that endures. It is older than mountains, older than oceans, older than life itself. It has witnessed the entire history of the planet, from the fiery chaos of the early Earth to the complex, living world we know today. It will continue long after we are gone, a silent guardian for whatever comes next. The field also reminds us of the interconnectedness of all things. The same iron that flows in the outer core is found in our blood, in the soil, in the rocks beneath our feet. The same forces that generate the magnetic field also drive plate tectonics, shape the landscape, and influence the climate. The field is not separate from the Earth, but an integral part of it, a manifestation of the planet's inner workings. And we, living on the surface, are part of that same system, connected by invisible threads to the core, the sun, and the cosmos beyond. The field's slow drift and occasional reversals are a reminder that change is natural, even on a planetary scale. Nothing is permanent, but nothing is lost either. The field has reversed hundreds of times, yet it has always returned, always continued. Each reversal is a transformation, not an ending. The field adapts, reorganizes, and persists. There is a lesson in this, that resilience is not about rigidity, but about flexibility, about the ability to change and yet remain. The field also teaches us patience. The processes that generate and sustain the magnetic field operate on timescales far beyond human perception. The convection currents in the outer core move at speeds of millimeters per year. A magnetic reversal unfolds over thousands of years. The field's strength varies on timescales of centuries. These are not things we can observe directly in a single lifetime, but we can measure them, study them, and understand them. The field invites us to think beyond the immediate, to consider the long view, to appreciate the slow, steady rhythms of the planet. The field is also a reminder of the power of collaboration. Our understanding of the magnetic field is the result of centuries of work by countless scientists, from ancient Chinese scholars to modern geophysicists. Each generation has built on the discoveries of the previous one, refining measurements, developing new theories, and exploring new questions. The field is a shared inheritance, a body of knowledge that belongs to all of humanity. It is a testament to what we can achieve when we work together, when we pool our observations and insights, when we seek to understand the world not for personal gain, but for the simple joy of knowing. The field also has a role in our sense of place. Knowing that the Earth is a magnet, that invisible lines of force arc through the sky above us, that particles from the sun are constantly interacting with our planet's magnetic shield, all of this enriches our experience of being here, on this particular world, at this particular time. It deepens our connection to the planet, reminding us that we are not just on the Earth, but part of a dynamic, interconnected system that stretches from the core to the edge of space. The field is also a source of quiet awe. It is one of those phenomena that, the more you learn about it, the more remarkable it becomes. The fact that a planet can generate its own magnetic field, that this field can extend hundreds of thousands of kilometers into space, that it can trap particles and create glowing lights in the sky, that it can reverse polarity and yet persist, all of this is astonishing. And yet it happens quietly and continuously, without any need for our attention or approval. The field is a reminder that the universe is full of wonders, many of them hidden in plain sight, waiting to be discovered by those who take the time to look. The field also offers a sense of continuity. The same magnetic field that guides a compass today guided explorers centuries ago. The same field that creates auroras now created them for our ancestors, who watched the lights dance across the sky and wove stories to explain them. The field connects us to the past and to the future, a thread of continuity running through the generations. It is a reminder that we are part of a long story, that our lives are brief chapters in a much larger narrative. The field also encourages humility. Despite all we have learned, there is still much we do not know. The exact timing of the next reversal, the detailed structure of the core, the full range of the field's effects on life and climate, these remain open questions. The field is a reminder that the universe is complex, that knowledge is hard-won, and that there is always more to learn. It invites us to remain curious, to keep asking questions, to keep exploring. The field is also a gift. We did not create it, we cannot control it, but we benefit from it every day. It shields us, guides us, and connects us to the cosmos. It is a legacy from the deep past, a product of the planet's formation and evolution, and it will continue into the deep future. The field is a reminder that we are the recipients of countless gifts, from the air we breathe to the ground we walk on, and that our task is not to possess or dominate, but to understand, appreciate, and protect. The field also invites us to slow down. In a world that often feels rushed and chaotic, the magnetic field operates on timescales that are slow, steady, and patient. It does not hurry. It does not panic. It simply is doing its work quietly and continuously. There is something deeply calming about this. It is a reminder that not everything needs to happen quickly, that some of the most important processes unfold slowly, over years, centuries, millennia. The field teaches us the value of patience, of persistence, of the long view. The field also connects us to the stars. The same processes that generate Earth's magnetic field also operate in other stars, in other planets, in distant corners of the galaxy. Magnetic fields are a universal phenomenon, a fundamental aspect of how matter and energy interact. By studying Earth's field, we gain insights that apply far beyond our own planet. The field is a local example of a cosmic principle, a window into the workings of the universe. It is a reminder that we are not isolated, but part of a vast, interconnected cosmos. The field also has a role in our sense of wonder. The fact that something so powerful and important can be invisible, intangible, and yet utterly real challenges our assumptions about what is significant. It reminds us that the most important things are not always the most obvious, that the world is full of hidden depths, and that understanding requires more than just looking. It requires thinking, measuring, questioning, and imagining. The field is a testament to the power of human curiosity and intellect, to our ability to perceive and understand things that lie beyond the reach of our senses. The field also offers a sense of safety. Knowing that the Earth has a magnetic shield, that it has protected life for billions of years, that it continues to do so today, is deeply reassuring. We live in a universe that can be harsh and unforgiving, but we are not unprotected. The field is a buffer, a guardian, a quiet presence that stands between us and the more hostile aspects of space. It is a reminder that we are, in a very real sense, cared for by the planet we call home. The field also reminds us of the importance of the unseen. So much of what matters in life is invisible. Love, trust, knowledge, memory, intention. The magnetic field is another example of this. It cannot be seen, but it shapes our world in profound ways. It is a reminder to pay attention to the invisible, to value what cannot be directly perceived, to recognize that reality is deeper and richer than appearances suggest. The field also has a role in our sense of time. By providing a record of Earth's history, by marking the passage of millions of years, the field gives us a way to orient ourselves in deep time. It is a clock, a calendar, a timeline written in stone. It helps us understand where we are in the long story of the planet, and it gives us perspective on our own brief existence. The field is a reminder that we are part of something much larger and older than ourselves, and that our actions have consequences that ripple through time. The field also invites contemplation. There is something meditative about thinking about the magnetic field, about imagining the slow churn of molten iron deep below, the invisible lines of force arcing through space, the particles spiraling along those lines, the auroras glowing in the night sky. It is a subject that rewards quiet reflection, that opens up vistas of thought and feeling. The field is not just a scientific fact, but a doorway to wonder, a starting point for deeper questions about the nature of reality, the origins of the universe, and our place within it. The field also connects us to the elements. Iron, the metal at the heart of the geodynamo, is forged in the cores of dying stars, scattered into space by supernovae, and gathered into new planets as solar systems form. The iron in Earth's core, the iron in our blood, the iron in the rocks beneath our feet, all of it has a cosmic origin. The magnetic field is a reminder of this deep connection, this thread that links us to the stars. We are made of stardust, and the field is one of the ways that stardust continues to shape our world. The field also offers a sense of balance. It is strong enough to protect us, but not so strong as to be oppressive. It is dynamic enough to be interesting, but stable enough to be reliable. It changes but slowly. It drifts but predictably. The field is a model of moderation, of balance, of the middle way. It is neither too much nor too little, but just right for the needs of life on Earth. The field also has a role in our sense of belonging. Knowing that we are enveloped by the magnetic field, that it extends above us and below us, that it connects us to the core of the planet and to the space beyond, gives us a sense of being held, of being part of something larger. It is a reminder that we are not alone, not isolated, but embedded in a web of connections that span scales from the atomic to the planetary to the cosmic. The field also teaches us about emergence. The magnetic field is not imposed from outside, but arises naturally from the motion of conducting fluid in the core. It is an emergent property, a pattern that appears when the conditions are right. This is a powerful idea, that complexity and order can arise spontaneously from simpler processes, that the whole can be more than the sum of its parts. The field is an example of this principle in action, a reminder that the universe is creative, that it generates novelty and structure without any need for external direction. The field also invites gratitude. It is easy to take the magnetic field for granted, to forget that it is there, to overlook its role in making Earth habitable. But when we pause to consider it, when we reflect on what it does and how it works, a sense of gratitude naturally arises. The field is a gift, and recognizing it as such enriches our experience of being alive on this planet. The field also offers a sense of continuity with the past. The same magnetic field that exists today has existed, in some form, for most of Earth's history. It has been a constant presence, a silent witness to the rise and fall of species, the shifting of continents, the ebb and flow of ice ages. The field is a link to the deep past, a reminder that we are part of a long, unbroken chain of existence that stretches back billions of years. The field also points toward the future. As long as the core remains molten and convecting, the magnetic field will persist. It will continue to protect Earth, to guide compasses, to create auroras. It will outlast us, outlast our civilizations, outlast perhaps even our species. The field is a reminder that the planet has a future, that the story is not over, that there is more to come. It is a source of hope, a promise of continuity, a reason to care for the world we inhabit. The magnetic field that surrounds our planet extends its influence far beyond the boundaries we've already explored, reaching into the smallest scales of matter and the grandest architectures of the cosmos. Every atom, every molecule, every living cell exists within this gentle electromagnetic embrace. Even now, as you rest, the field passes through you, utterly harmless, utterly silent, a background hum in the language of physics that your body has always known. The iron in your blood, the same element that swirls in Earth's core, responds ever so faintly to magnetic forces, though you cannot feel it. This connection, invisible and ancient, links your physical form to the deepest layers of the planet beneath you. Magnetism itself is one of the fundamental forces of nature, woven into the fabric of the universe alongside gravity, the strong nuclear force and the weak nuclear force. It arises from a motion of electric charges, from the spin of electrons, from currents flowing through conductors. At the quantum level, magnetism is a manifestation of relativity and the structure of space-time itself. When an electron orbits an atomic nucleus, it creates a tiny magnetic field, a miniature dipole. When countless electrons align their spins in the same direction within a material, their individual fields combine, and the material becomes magnetic. This is how lodestones form, how the Earth's core generates its field, how the sun's turbulent plasma creates magnetic loops that arc millions of kilometers into space. The study of magnetism has a long and quiet history, stretching back thousands of years to the first observations of naturally magnetic rocks. Ancient Chinese scholars noticed that certain stones, when suspended freely, would align themselves in a north-south direction. This discovery, simple and profound, eventually led to the development of the compass, one of humanity's most enduring navigational tools. For centuries, sailors carried compasses across oceans, trusting the invisible hand of Earth's magnetic field to guide them home. The compass needle, a small piece of magnetized metal, is nothing more than a tiny bar magnet free to rotate. It aligns itself with the planet's field lines, always seeking the magnetic poles. In this way, the compass is a window into the invisible, a tangible connection to forces we cannot see but can trust completely. The word magnet itself comes from Magnesia, a region in ancient Greece where naturally magnetic stones were found. The Greeks called these stones magnetes lithos, the stone from Magnesia. Over time, the word evolved, and the phenomenon became known simply as magnetism. For much of human history, magnetism was a mystery, a force that seemed almost magical. Objects attracted or repelled each other without touching, without any visible connection. It was not until the 19th century that scientists began to understand the deep relationship between electricity and magnetism, two phenomena that had seemed entirely separate. In 1820, a Danish physicist named Hans Christian Ørsted made a discovery that would change the course of science. During a lecture demonstration, he noticed that a compass needle deflected when placed near a wire carrying an electric current. This was the first clear evidence that electricity and magnetism were related, that a moving electric charge could produce a magnetic field. Ørsted's observation was gentle, almost accidental, yet it opened the door to a new understanding of nature. Soon after, other scientists began to explore this connection. André-Marie Ampère in France developed mathematical descriptions of how currents produce magnetic fields. Michael Faraday in England discovered that a changing magnetic field could induce an electric current in a wire, the principle behind electric generators and transformers. Faraday's work was particularly elegant. He introduced the concept of field lines, imaginary lines that map the direction and strength of a magnetic field. If you've ever sprinkled iron filings around a bar magnet, you've seen these lines made visible. The filings align themselves along the field, tracing out smooth curves that loop from one pole to the other. Faraday imagined these lines as real entities, paths along which magnetic influence flowed. Though we now understand fields in more abstract terms, his visualization remains a powerful and calming way to think about magnetism. The lines are smooth, continuous, never crossing, always forming closed loops. They represent order and structure in the invisible world. James Clerk Maxwell, a Scottish physicist, took the work of Faraday, Ampère, and others and unified it into a single mathematical framework. His equations, published in the 1860s, describe how electric and magnetic fields interact, how they generate each other, how they propagate through space as electromagnetic waves. Maxwell's equations are among the most beautiful and profound achievements in physics. They reveal that light itself is an electromagnetic wave, a ripple of electric and magnetic fields traveling together through the vacuum. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays are all part of the same electromagnetic spectrum, differing only in wavelength and frequency. Magnetism, electricity, and light are all facets of a single, unified phenomenon. This unification was a moment of deep clarity in the history of science, a realization that seemingly separate forces were expressions of the same underlying reality. It is a reminder that nature, at its core, is simpler and more elegant than it first appears. The same principles that govern a compass needle also govern the light from distant stars, the warmth of the sun on your skin, the signals that carry information across the world. Everything is connected, woven together by the electromagnetic force. The Earth's magnetic field, as we've seen, is generated by the motion of molten iron in the outer core. But this is not the only way magnetic fields arise in nature. The sun, too, has a magnetic field, far more complex and dynamic than Earth's. The sun is a ball of plasma, a state of matter in which electrons are stripped from atoms, creating a sea of charged particles. These particles are in constant motion, driven by the sun's intense heat and rotation. As they move, they generate electric currents, and these currents produce magnetic fields. The sun's magnetic field is not a simple dipole like Earth's. It is tangled, twisted, and constantly changing, shaped by the turbulent convection of plasma beneath the solar surface. Sunspots, those dark patches that appear on the sun's surface, are regions where the magnetic field is particularly strong. The field is so intense that it inhibits the flow of heat from the sun's interior, making these regions cooler and darker than their surroundings. Sunspots often appear in pairs, with opposite magnetic polarities, connected by loops of magnetic field that arch high into the sun's atmosphere. These loops can be hundreds of thousands of kilometers long, large enough to swallow several Earths. Sometimes, the magnetic field lines become so twisted and stressed that they snap and reconnect in a process called magnetic reconnection. When this happens, enormous amounts of energy are released suddenly, producing solar flares and coronal mass ejections. Solar flares are intense bursts of radiation, visible across the electromagnetic spectrum from radio waves to gamma rays. They can disrupt communications on Earth, interfere with GPS signals, and pose a radiation hazard to astronauts in space. Coronal mass ejections are even more dramatic. They are massive clouds of plasma and magnetic field ejected from the sun's corona, traveling through space at speeds of hundreds or thousands of kilometers per second. When a coronal mass ejection reaches Earth, it can compress and distort our magnetosphere, triggering geomagnetic storms and producing brilliant auroras. These events remind us that the sun and Earth are not isolated, but are connected by the invisible threads of magnetic fields and the flow of the solar wind. The sun's magnetic field also follows a cycle, known as the solar cycle, which lasts about 11 years. During this cycle, the number of sunspots rises and falls, and the sun's magnetic field undergoes a complete reversal. At the beginning of the cycle, the sun's magnetic north pole points in one direction. By the end of the cycle, it points in the opposite direction. Then, over the next 11 years, it flips back again. This means the full magnetic cycle of the sun is actually 22 years long. The cause of this cycle is not fully understood, but it is thought to be related to the complex interplay of rotation, convection, and magnetic field generation in the sun's interior. The solar cycle is a reminder that magnetic fields are dynamic, living entities, constantly evolving and reshaping themselves. Beyond the sun, magnetic fields are found throughout the universe. Many planets have magnetic fields, generated by the motion of conducting fluids in their interiors. Jupiter, the largest planet in our solar system, has the strongest magnetic field of any planet, more than 10 times stronger than Earth's. Jupiter's field is generated by the motion of metallic hydrogen in its deep interior, where pressures are so extreme that hydrogen behaves like a liquid metal. The field extends millions of kilometers into space, far beyond the planet's visible surface, creating a vast magnetosphere that traps charged particles and produces intense radiation belts. Jupiter's magnetosphere is so large that if we could see it from Earth, it would appear several times bigger than the full moon. Saturn, too, has a magnetic field, though it is weaker than Jupiter's. What makes Saturn's field unusual is that it is almost perfectly aligned with the planet's rotation axis, unlike Earth's field, which is tilted. This near-perfect alignment is a puzzle for scientists, as it suggests that the processes generating Saturn's field are somehow different from those on Earth or Jupiter. Uranus and Neptune also have magnetic fields, but theirs are highly tilted and offset from the planet's centers, creating complex and asymmetric magnetospheres. These distant ice giants remind us that magnetic fields come in many forms, shaped by the unique conditions within each planet. Not all planets have magnetic fields. Venus, similar in size and composition to Earth, has no global magnetic field. Its core may be solid, or its rotation may be too slow to generate a dynamo. Mars once had a strong magnetic field, as evidenced by magnetized rocks in its ancient crust, but the field disappeared billions of years ago, perhaps when the planet's core cooled and solidified. Without a magnetic field, Mars lost much of its atmosphere to the solar wind, and its surface became the cold, dry, barren place we see today. The presence or absence of a magnetic field can profoundly affect a planet's evolution and its ability to support life. Moons, too, can have magnetic fields, though they are rare. Ganymede, the largest moon of Jupiter, is the only moon in the solar system known to have its own magnetic field. This field is thought to be generated by a dynamo in a layer of liquid iron deep within the moon. Ganymede's field creates a small magnetosphere nested within Jupiter's much larger one, a magnetic bubble within a bubble. This discovery was surprising, as moons are generally too small and cold to sustain the kind of internal motion needed for a dynamo. Yet, Ganymede defies expectations, quietly generating its own magnetic shield. Stars beyond our Sun also have magnetic fields. Many stars, especially young and rapidly rotating ones, have strong fields that shape their atmospheres and drive powerful stellar winds. Neutron stars, the collapsed cores of massive stars that have exploded as supernovae, have the strongest magnetic fields known in the universe. A neutron star is incredibly dense, packing more mass than the Sun into a sphere only about 20 kilometers across. As the star collapses, its magnetic field is compressed and amplified to extraordinary strengths, trillions of times stronger than Earth's field. Some neutron stars, called magnetars, have fields so intense that they warp the very fabric of space-time around them and can trigger sudden bursts of X-rays and gamma rays. These objects are among the most extreme environments in the cosmos, places where the laws of physics are pushed to their limits. Magnetic fields also play a role in the formation of stars and planets. In the vast clouds of gas and dust that fill interstellar space, magnetic fields thread through the material, influencing how it collapses under gravity. When a cloud begins to contract to form a new star, the magnetic field can slow the collapse, support the cloud against gravity, and help regulate the flow of material. As the cloud spins faster, it flattens into a disk, and the magnetic field helps transport angular momentum outward, allowing material to fall inward onto the growing star. In the disk, magnetic fields can also affect the formation of planets, influencing how dust grains stick together and how gas is distributed. The magnetic field is a sculptor, shaping the birth of stars and worlds. Galaxies, too, have magnetic fields. Our Milky Way galaxy is permeated by a weak but extensive magnetic field that threads through the spiral arms and the space between stars. This galactic magnetic field is generated by the collective motion of charged particles and the turbulent dynamics of interstellar gas. It plays a role in shaping the structure of the galaxy, influencing the paths of cosmic rays and affecting the formation of new stars. Observing galactic magnetic fields is challenging, as they are very weak and difficult to detect, but astronomers have mapped them using observations of polarized light from stars and radio emissions from interstellar gas. These maps reveal a complex, tangled structure, a magnetic web that spans the entire galaxy. Even the space between galaxies is not entirely empty. It contains a thin plasma, and this plasma carries magnetic fields with it. These intergalactic magnetic fields are extremely weak, but they extend over vast distances, connecting galaxies and galaxy clusters. The origin of these fields is still a mystery. They may have been generated in the early universe, or they may have been produced by outflows from galaxies. Studying intergalactic magnetic fields helps us understand the large-scale structure of the universe and the processes that shape it over cosmic time. Magnetism is also intimately connected to the phenomenon of superconductivity. A superconductor is a material that, when cooled below a certain temperature, loses all electrical resistance. Current can flow through a superconductor indefinitely without any loss of energy. Superconductors also have a remarkable property called the Meissner effect. They expel magnetic fields from their interior. If you place a superconductor in a magnetic field and then cool it below its critical temperature, the field is pushed out and the superconductor becomes perfectly diamagnetic. If you place a small magnet above a superconductor, the magnet will levitate, floating in midair as the superconductor repels the magnetic field. This levitation is silent, stable, and strangely beautiful, a visible manifestation of quantum mechanics at work. Superconductivity is a quantum phenomenon arising from the collective behavior of electrons in the material. At low temperatures, electrons pair up and move together in a coordinated way, forming a quantum state that cannot be disrupted by the usual sources of resistance. Superconductors have many practical applications, from powerful electromagnets used in MRI machines and particle accelerators to sensitive detectors of magnetic fields. Researchers are also working to develop superconductors that work at higher temperatures, which would make them easier and cheaper to use. The dream of room temperature superconductivity remains elusive, But progress continues, and each step forward brings us closer to a future where superconducting technology is commonplace. Magnetic resonance imaging, or MRI, is one of the most important medical applications of magnetism. An MRI machine uses a strong magnetic field, typically 1 to 3 Tesla, to align the magnetic moments of hydrogen nuclei in the body. Radio waves are then used to disturb this alignment, and as the nuclei relax back into alignment, they emit signals that can be detected and used to create detailed images of internal tissues. MRI is non-invasive and does not use ionizing radiation, making it safer than X-rays or CT scans for many purposes. It can reveal soft tissues, organs, blood vessels, and even the structure of the brain with remarkable clarity. The development of MRI was a triumph of physics and engineering, and it has transformed medicine, allowing doctors to diagnose and treat diseases with unprecedented precision. The magnetic moments of atomic nuclei are incredibly small, but they can be measured with great sensitivity. Nuclear magnetic resonance, or NMR, is the underlying principle behind MRI, and it is also a powerful tool in chemistry and material science. By studying how nuclei respond to magnetic fields, scientists can learn about the structure of molecules, the arrangement of atoms, and the dynamics of chemical reactions. NMR spectroscopy has been used to determine the structures of countless compounds, from simple organic molecules to complex proteins and DNA. It is a quiet, patient technique, revealing the hidden architecture of matter one signal at a time. Animals, as we've discussed, use Earth's magnetic field for navigation, but the mechanisms by which they sense the field are still being explored. One leading hypothesis involves a protein called cryptochrome, found in the eyes of birds and other animals. Cryptochrome contains a pair of electrons that can exist in a quantum-entangled state, and the Earth's magnetic field may influence the probability of certain chemical reactions involving these electrons. This influence could produce signals that the animal's brain interprets as information about direction. If true, this would mean that migratory birds navigate using quantum mechanics, a delicate interplay of light, magnetism, and chemistry. The idea is still being tested, but it is a beautiful example of how nature may exploit quantum phenomena for practical purposes. Magnetism also plays a role in the behavior of certain bacteria. Magnetotactic bacteria are microorganisms that contain chains of tiny magnetic crystals called magnetosomes. These crystals, made of magnetite or another magnetic mineral, act like internal compass needles, allowing the bacteria to orient themselves along magnetic field lines. This ability helps them navigate through sediments and water to find regions with optimal oxygen levels. Magnetotactic bacteria are found in aquatic environments around the world, from freshwater ponds to deep ocean sediments. They are a reminder that even the smallest forms of life are attuned to the planet's magnetic field, using it to survive and thrive. The study of magnetism has also led to the development of magnetic materials with remarkable properties. Permanent magnets, made from alloys of iron, cobalt, nickel, and rare earth elements, are used in countless devices, from electric motors and generators to loudspeakers and hard drives. The strength of a permanent magnet depends on the alignment of magnetic domains within the material. When a material is magnetized, the domains align, and their individual fields add together. If the domains are randomly oriented, the fields cancel out, and the material is not magnetic. Creating strong permanent magnets requires careful control of the material's composition and structure, and advances in material science have led to ever more powerful magnets. Electromagnets, on the other hand, generate magnetic fields using electric currents. When current flows through a coil of wire, it creates a magnetic field along the axis of the coil. The strength of the field can be increased by wrapping the coil around a core made of a ferromagnetic material, like iron. Electromagnets have the advantage that their fields can be turned on and off, and their strength can be adjusted by changing the current. They are used in a wide range of applications, from industrial, lifting magnets and magnetic separators, to scientific instruments and experimental fusion reactors. The largest electromagnets ever built are found in particle accelerators, where they guide beams of charged particles along circular paths at speeds close to the speed of light. Magnetic levitation, or maglev, is a technology that uses magnetic fields to lift and propel vehicles without physical contact with the track. Maglev trains float above the guideway, supported by magnetic repulsion or attraction, and are driven forward by electromagnetic forces. Because there is no friction between the train and the track, maglev trains can travel at very high speeds, smoothly and quietly. Several maglev systems are in operation around the world, and they represent a glimpse of a future where transportation is faster, cleaner, and more efficient. The sensation of riding a maglev train is uniquely serene, a glide above the ground with almost no vibration, as if the vehicle is suspended in a gentle magnetic embrace. Magnetic fields are also used to confine and control plasmas in experimental fusion reactors. Nuclear fusion, the process that powers the sun, involves fusing light atomic nuclei together to form heavier nuclei, releasing enormous amounts of energy. To achieve fusion on Earth, scientists must heat a plasma to temperatures of millions of degrees and hold it together long enough for fusion reactions to occur. Because no material can withstand such temperatures, the plasma must be confined using magnetic fields. In a tokamak, a type of fusion reactor, powerful magnetic fields shaped like a donut trap the plasma and keep it away from the walls of the reactor. Achieving sustained fusion is one of the great challenges of modern science, but progress is being made, and the dream of clean, abundant fusion energy draws closer. Magnetic fields also influence the behavior of charged particles in space. Cosmic rays, high-energy particles from outside the solar system, are deflected by magnetic fields as they travel through the galaxy. The Earth's magnetic field shields us from some of these particles, and the Sun's magnetic field, carried by the solar wind, creates a boundary called the heliosphere that protects the solar system from interstellar cosmic rays. Spacecraft traveling beyond the planets eventually cross the heliopause, the edge of the heliosphere, and enter interstellar space, where the influence of the Sun's magnetic field fades and the galactic magnetic field takes over. Voyager 1 and Voyager 2, launched in 1977, have both crossed this boundary, becoming the first human-made objects to reach interstellar space. They continue to send back data, revealing the properties of the magnetic field and plasma in this distant, quiet realm. The interaction between magnetic fields and charged particles also produces phenomena called plasma waves. These are oscillations in the density and magnetic field of a plasma, analogous to sound waves in air or water waves on the ocean. Plasma waves can transport energy and momentum, and they play a role in many processes in space, from the acceleration of particles in the magnetosphere to the heating of the solar corona. Some plasma waves can be converted into sound waves that we can hear. NASA has recorded these waves using instruments on spacecraft and converted them into audio files. The sounds are eerie and otherworldly, a chorus of whistles, chirps, and hums, the voice of the magnetosphere singing in the language of plasma and magnetism. Magnetic fields are also important in the study of Earth's interior. By measuring the magnetic properties of rocks and minerals, geophysicists can learn about the conditions deep within the planet. The temperature, pressure, and composition of the core affect how the geodynamo operates and how the magnetic field is generated. Variations in the magnetic field at the surface provide clues about the flow of molten iron in the outer core and the structure of the mantle. Magnetic surveys, conducted from the ground, from aircraft, and from satellites, map the magnetic field in detail, revealing patterns and anomalies that tell stories of tectonic activity, volcanic eruptions, and the movement of continents over millions of years. The magnetic field also records the history of Earth's climate. Tiny magnetic particles in sediments and ice cores align themselves with the field as they settle, and by studying these alignments, scientists can reconstruct how the field has changed over time. This information, combined with other geological and paleoclimate data, helps us understand the long-term evolution of Earth's environment and the forces that have shaped it. The magnetic field is a silent witness to the planet's history, a record written in iron and stone. In our modern world, magnetism is everywhere, woven into the fabric of daily life. The electric motors that power appliances, vehicles, and industrial machinery rely on magnetic fields to convert electrical energy into motion. Generators use magnetic fields to convert motion into electrical energy, providing the power that lights our homes and runs our devices. Transformers use magnetic fields to change the voltage of alternating current, making it possible to transmit electricity efficiently over long distances. Credit cards and magnetic strips store information using patterns of magnetization. Hard drives and magnetic tapes use tiny magnetic domains to encode data, preserving our digital memories. Even as newer technologies like solid-state drives replace magnetic storage in many applications, the principles of magnetism remain foundational to modern technology. Magnetic sensors detect position, speed, and orientation in countless devices, from smartphones and car engines to industrial robots and medical equipment. Magnetic materials are used in wireless charging systems, where magnetic fields transfer energy between coils without physical contact. The future will undoubtedly bring new applications of magnetism, as researchers continue to explore the properties of materials and the possibilities of quantum technologies. There is something deeply reassuring about the constancy of magnetic fields, their quiet presence in the background of existence. They do not demand attention. They do not shout or flash. They simply are, always there, always working, shaping the world in subtle and profound ways. The compass needle that points north, the aurora that dances in the polar sky, the invisible shield that protects us from the solar wind, all are expressions of the same fundamental force, a force that has been with us since the beginning and will remain long after we are gone. As you rest now, you can imagine the magnetic field lines threading through the earth, looping from pole to pole, extending far into space. You can picture the currents of molten iron flowing in the core, driven by heat and rotation, generating the field that has guided travelers, inspired scientists, and protected life for billions of years. You can think of the sun, its magnetic field twisting and snapping, sending waves of plasma toward us, only to be deflected by our planet's magnetic embrace. You can envision the galaxies, each one a swirl of stars and gas and magnetic fields, connected by invisible threads across the vastness of space. Magnetism is one of the fundamental ways the universe organizes itself, a force that binds atoms, shapes planets, and structures galaxies. It is both powerful and gentle, capable of lifting trains and guiding butterflies. It is ancient, arising from the motion of charges and the spin of particles, yet it is ever present, surrounding us, passing through us, connecting us to the cosmos. In understanding magnetism, we understand a little more about the nature of reality, the hidden patterns that govern the world we see and the worlds we cannot see. And so, as the night deepens and your thoughts begin to drift, let the knowledge of magnetic fields be a source of comfort. Let it remind you that you are part of something vast and orderly, a universe governed by laws that are beautiful and comprehensible. Let it remind you that even in the darkness, there are forces at work, invisible and tireless, holding everything together. The Earth's magnetic field has cradled life for eons, and it will continue to do so, a silent guardian, a gentle presence, a reminder that we are never truly alone. There's no need to hold on to these thoughts too tightly. Let them settle softly into your mind, like snow falling on a quiet field. Let the images of field lines, auroras, and spinning cores fade in the background, becoming part of the peaceful landscape of sleep. The science will still be there tomorrow, waiting patiently for you to return, but for now, it has done its work. It has carried you through a journey of discovery, and now it invites you to rest. The magnetic field asks nothing of you. It does not need your attention or your understanding to continue its work. It will go on, as it always has, shaping the space around the Earth, guiding particles, creating beauty, protecting life. And you, safe within its invisible embrace, can let go of the day, let go of your thoughts, and simply be. You are held by the planet, by the field, by the quiet forces that make existence possible. You are exactly where you need to be. If you are still awake, know that there are countless more stories like this one, more journeys through the wonders of science, more gentle explorations of the universe. They will be here, waiting for you, whenever you wish to return. But for now, there's only this moment, this breath, this soft and quiet space where knowledge and rest meet. There is only the field, the earth, the night, and you. Sleep well, dear listener. Let the magnetic field carry you into dreams. Let the currents of the earth's core hum a lullaby too deep to hear. Let the auroras paint the inside of your eyelids with soft colors. Rest in the knowledge that you are part of a vast and beautiful system, a universe that holds you gently. Rest in the certainty that the field will be here when you wake, and the science will still be true, and the world will still turn. Rest now, and let the magnetism of the earth remind you that everything is connected, everything is cared for, and everything, including you, is exactly as it should be. Good night.